Hi guys, on the website for this session you'll find a table with all the operators in C that you can use for expressions, and this table also contains the precedence of each operator and its so-called associativity. Now the precedence is important in order to know where do you have to put parentheses or where is the operator precedence taking care of such a thing. And the associativity is important to understand whether an expression is evaluated from left to right or from right to left. So actually this table is sufficient to use expressions in C, but I also use this opportunity to introduce you with a more formal description of such things with so-called production rules. And with these production rules, I also describe in general the structure of a program, also for example the grammar that is required for, let's say, the instruction set architecture description for the ULM generator, so that we can more precisely and more formally describe what structure is expected by a parser, the parser of the C compiler, the parser of the ULM generator, and so on. First of all, we will just deal with tokens. So we already assume that some lexical analysis happened, and in this example I just use two kinds of tokens, punctuator and actually just one, the plus operator, and identifiers, like for example in C. But in the example actually I just will use single characters for an identifier, for example A or B and so on. That means if I have an expression like that, A plus B plus C, then this was already tokenized. And to make it clear in the example what is a token, I usually will put a box around it. So you see that I just have this sequence of tokens, an identifier followed by a punctuator and so on. Now in a first grammar I want to specify that this here would be a legal expression consisting of just one identifier. Also, this here identifier plus identifier should be allowed, and actually an arbitrary sum of identifiers should be allowed. So this should be allowed. But for example, something like A plus plus should not be allowed. And of course, we again just consider here the tokens. In this case, one symbol represents exactly one kind of token. Makes it simpler, but identifiers could be specified like in C. Now for specifying this grammar, I also will use symbols, and I have somehow to distinguish the symbols from the symbols for the tokens. And for that I will use, like on the website, these angles. So for example, this here is a symbol used for describing the grammar. And now come the production rules. This symbol can be replaced or can produce other symbols of the grammar or the tokens. So we deal with a set of symbols from the tokens and a set of symbols defined in the grammar. Now such a simple expression in the grammar can, for example, produce a symbol specified in the grammar called term. And the second rule will say that a term can produce, for example, an identifier. So this goes into a box. But this is actually not the complete first rule. Such an expression also can produce an expression followed by the plus punctuator followed by the term. So it can produce a symbol from the grammar, a symbol from the tokens, and a symbol from the grammar. And now we can check out that you, for example, here I should have written not allowed, that you can produce all these sequences of tokens with these rules, but you cannot produce the sequence. And this is the first step to see how a parser, if a parser can somehow implement these rules, could give us here a syntax error. And here it could check that it's correct. You will see it also will allow to evaluate actually such expressions. So how could we produce this token? Of course, by starting with an expression, and actually this will be used as the so-called start symbol of this grammar. This then would produce a term, and this then would produce an identifier, and this here can be any identifier, in this case, for example, A. So this means, check, this is producible by this grammar, and therefore it belongs to the language, the formal language specified by this grammar. But we also could have used a different rule in the beginning to produce this. Let me show you that. I want to have here the space. If I would have used the second rule, you can read this, an expression can produce a term, or an expression can produce an expression followed by a plus, followed by a term. If I would have used this second rule, that it's producing an expression followed by the plus punctuator, followed by a term, then in the next step I could have used the first rule again, this rule, to replace this expression with a term, followed by the plus, followed by the term. I do not change this, I just expand this to the term. And then I could have replaced here this term with an A in the box. I copy paste this plus in the box, and this second term would be replaced with a B. So also this belongs to the language specified by this grammar. Let's check out this expression. And there I could have expanded in this, after this first expansion, this expression again with this second rule here. And then I would have gotten in a second expansion an expression followed by the plus token, followed by a term, followed by a plus token, followed by a term. Then of course this can just be replaced with a term, and then you see actually after one other step I can replace this first term with an A in the box, plus in the box, B in the box, plus in the box, C in the box. So nothing complicated. So of course this also belongs to the language. In this example it's also obvious that this sequence of tokens cannot be produced. If you produce two plus punctuators, then you always have in between at least one identifier, actually exactly one identifier. So to understand actually at this point how to detect what is not producible is not what you're focusing right now. For you, the focus should be to understand that this grammar specifies for you what is allowed, what is accepted, that you can have an identifier or a sum of identifier, and the meaning of that is not just given by these three examples, it's given here a bit more general. And you also will see that with these grammar rules, you can get an idea how expressions are actually evaluated. I will now again produce some sequence of tokens and show you how this can be represented in a tree structure. So I begin, for example, with producing from an expression followed by the plus token, followed by a term. And in a tree structure, I could represent what was produced as follows. I have a node labeled with the plus operator, and it has two child nodes. One is the expression on the left, and one the term on the right. And then in a second step, I produce from this expression just a term, and the rest I just copy paste. And that means that here this node has another child node, which is this term. And then in the next step, I actually do two steps. I produce from this, for example, the identifier A, then I copy paste this here, and then I produce from that the identifier P. Then I would have this here. And actually, this can be written differently, shorter. I just could say, I'm just interested in the tokens, in the punctuators for knowing what operation needs to be carried out on the operands, which are the identifiers. So you see that with this rules, basically you say that A plus B, that's what you type in, some program text, could be internally represented by such a tree structure. Now the important thing is to see what happens if you have A plus B plus C. So basically I have to figure out how to expand an expression into, in the end, the token A, followed by plus, followed by B, followed by plus, followed by C. And I will just do this by basically trial and error, or the strategy is actually that after first expansion, this will be just an expression, followed by the plus, followed by the term, which I then replace into C. So I think here trial and error is a good approach in the beginning. So I expand this expression into that. And then I already could expand this into a C. And then I expand this expression here into another expression, followed by plus, followed by term. And then I copy paste this part. And then of course I can expand this expression into just another term. And the rest is copy paste. And now let's see how a tree structure would have been generated. The first node from here. So we have one node, plus node with the left and the right child. Let's actually begin here with the right child. That's this term here, which then in the end becomes this C. So that's how this would look like in the end. And the left child would be first this expression, which then gets expanded into this expression, which then gets expanded into this expression, which then generates this part. And that means the left child would look like that. Now, for evaluating such an expression, you start here at the root node and then evaluate it recursively, for example. That means I have to add the result of the left-hand side with the result of the right-hand side, or the value of the left-hand side with the value of the right-hand side. For getting the value on the left-hand side, I first have to use the value here in this node on the left-hand side, add to it the value on the right-hand side, and then you see this recursive structure. And if we now think about C, then each of these identifiers also has a type. Then we could, for example, think of A here being some signed integer, and B also some signed integer, but of type long. Then you might have different sizes. This might have 2 bytes and this 4 bytes. And then if you think about the C compiler doing certain bookkeeping and having a tree structure like that, which is used for recursively evaluating the expression, then you will also understand so-called implicit conversion rules that are applied when you evaluate an expression. That means for evaluating this node, the common type of A and B will be used. A will be, for example, converted into long, and B is already a long, and then you do the operation with the common type. And there will also be a rule for the case that, for example, A is unsigned and B is signed. Then the rule will be unsigned wins. So that means A is taken as it is, B will be implicitly converted to unsigned, and then the operation carried out with the implicitly converted operands. And you also see the order in which this operation gets carried out. First a plus b gets computed, and then you add to the result c. Now, this here, the later one, that you actually will evaluate a plus b plus c like a plus b inside of parentheses, and then you add c, means that this grammar specifies that the plus operation is left associative. That means you carry out this from left to right. Let's change this grammar rule a bit. I will not completely redo this example, but show you just how you can see this associativity in a grammar. If I would have specified the grammar as follows, first I also just state a production rule that an expression can be producing a term, but it also can produce a term followed by the plus punctuator followed by an expression. And you see I just flipped here the grammar symbols, and the rest is the same. A term can be a literal. Then if you would have a plus b plus c, and these are all tokens, you also first have to apply this second rule. So you would expand an expression into a term, followed by the plus operator, followed by an expression. And then you would replace this here again with a term followed by an expression, and that would give us this. And then in one further step, this last expression just gets be expanded in a term again. And from that you can produce here an A, the next term becomes the B, and so on. Now, you see, from this here we get also some initial node in the tree with a plus as root node. The left child would be this term, which in the end would be this A. So we would end up with that. Here we produce this, which produces this, which produces this, which means that the right child would be this node with B and C as a child. And that means with that grammar and rules for building the tree and using these trees for evaluating the expression, you would evaluate this operation from right to left. So you would say that in this case, A plus B plus C would be the same as A plus B plus C in parentheses. And that means you first have to compute that, and then you can compute the complete sum. And in this case, you would say that this grammar specifies that the plus operator is right associative. And these terms, left and right associative, you see in this table. Let me also show you how in the grammar you can specify that, for example, the precedence of the multiplication operator, the asterisk, is higher than the precedence of the plus operator. For that I make a more complex rule. So this is the second grammar. And there I say that an expression can be just a term. An expression also can be an expression followed by a plus. So I now have, in addition, the operations not only just plus, but also multiplication. So these are the legal operators, followed by a term. So I again go back to the left associativity. That's how it's defined in C. And now I specify a new rule for the term. And here I specify that the term can be a factor. It also can be a term followed by the asterisk for multiplication, followed by a factor. And a factor can be literal. And now we look at an example where it actually matters. So that means we have at least 3 identifiers, A plus B times C. If plus and multiplication would have the same precedence, then we here first would add A plus B and then multiply the result with C. But this will not happen in this case, because in order to represent this sequence of tokens, beginning with this expression, with this start symbol in the grammar, I first have to somehow produce this plus. Otherwise, I will not be able to produce this sequence of tokens. So I have to use the rule, because I have something on the left and right side, of course, of the plus operator. I have to use the rule that an expression can become an expression followed by the plus token, followed by a term. And then from this here, I can produce just a term, and from that, I can produce the A. Let's speed here things a bit up. So I end up here with the token A, followed by plus, followed by a term. And this means the first node in this tree, the root node, will actually be this plus, with the left child being A, and the right child comes from here. Now here I have to produce, of course, this asterisk. So for that I use this rule that the term can be a term followed by an asterisk followed by a factor. And then of course from this term I produce just a factor, and from this factor B, and from this factor C. So this will produce A followed by plus, followed by B, followed by the asterisk, followed by C. But you see that this here also generates a new node, the child node here, the asterisk, which has B as left child and C as right child. And now, in order to evaluate the value of this tree, you begin here, add the value from the left child to the value of the right child. That means for the value of the right child, you first have to get the value of this by multiplying the value of B with the value of C. And then, of course, you see these rules can also be expanded to, for example, support parentheses, and of course, all the operators specified in the C syntax.